All right, let's get right into it. Neuroimaging. I mean, it gives us this absolutely incredible window into the human brain. But here's the thing. The integrity of massive, multi-million-dollar studies, and honestly, years of research, often comes down to something we barely talk about: the quality of the raw images themselves. And that leads to a pretty high-stakes question, doesn't it? Because this actually happens. A subtle blur, a faint little ghost in the image, these aren't just small cosmetic issues. They can be seeds of doubt that completely corrupt our scientific conclusions. So the bottom line is this: bad data in means bad science out. It's that simple. It can send researchers down a completely wrong path, trying to explain brain differences that are, in reality, just noise in the machine. And that's why having rigorous, objective quality control isn't just a nice-to-have, it is absolutely essential. Now, to really get a handle on the solution, we first have to meet the villains of this story. Let's take a look at some of the common artifacts that can, well, haunt a brain scan. Okay, take a look at this. This is a perfect example of a classic zipper artifact. You see that distinct line zipping right across the image? It's basically electronic noise, and it's often caused by something as simple as the scanner room door not being sealed perfectly, which lets outside radio frequencies leak inside. But it's not just the equipment. Sometimes the issue comes from the participant themselves. Think about something as common as dental work. The metal in implants or braces. It's a huge problem for an MRI. It can cause major signal loss and warp the image, making it totally impossible to analyze any of the nearby brain regions. And get this, even our own biology can be a problem. If you look at that hazy, kind of smeared signal on the sides of this image, what you're seeing is the result of eye movements. Yep, even tiny, involuntary flickers of the eyes during a scan can cause the signal to spill over, basically contaminating the rest of the image. So the big question is, how do we catch these flaws systematically, especially when we're dealing with massive data sets, thousands of scans? Just relying on human eyes alone is way too slow, and frankly, it's pretty subjective. What we really need is an automated detective. And that detective has a name: MRI-QC. It's an open-source tool that's been designed to automatically process a brain image and pull out objective metrics about its quality. This is how we move away from just eyeballing it, which can be really inconsistent. So how does it work? Well, MRI-QC works by calculating dozens of what are called image quality metrics, or IQMs. The best way to think about these is like a scan's vital signs. They're objective numbers that describe very specific things about the image's quality. And believe me, it is incredibly thorough. It calculates things like the signal-to-noise ratio to measure how clear the image is. It measures blurriness, it looks for those ghosting artifacts, and it even checks how well you can tell different brain tissues apart. It basically generates a comprehensive report card for every single scan. Okay, this all sounds great, right? We've got the numbers, we've got the data, problem solved. Well, not so fast. Here comes the twist in our story. The numbers themselves, they have a hidden flaw. See, the vast majority of these IQMs are what's known as no reference. What that means is there's no universal perfect score. We can't compare a scan to some flawless, ground truth version of that same person's brain because, well, a perfect version doesn't exist. And don't just take my word for it. The researchers behind MRIQ put it perfectly. They said that because these are no reference metrics, there are no absolute universal thresholds to automatically say this is good versus this is bad. Let's try an analogy. Imagine two students from two totally different schools each get a score of 0.8 on a test. Is that a good score? You have no idea, right? Maybe school A's test was insanely difficult, and 0.8 is the best score in the entire class. Or maybe school B's test was super easy, and 0.8 is actually a failing grade. So that's the crucial point here. A number without context is pretty much meaningless. The exact same IQM value from two different scanners might mean two completely different things about image quality. To make any sense of the data, we need that missing context. This is where the second part of our solution comes into play. If MRIQC is the detective that gathers all the evidence, all those numbers, then QM Tools is the system that helps us actually interpret that evidence. QM Tools is a set of programs built to work hand in hand with the output from MRIQC. Its entire job is to solve that no-reference problem by giving us powerful ways to compare and contextualize all those quality metrics. So here's how this suite builds that all-important context. First, a tool called QM Traffic acts like a local grade curve. It shows you which of your own scans are outliers compared to the rest of the scans in your study. Next, QM Fetcher does something incredible. It reaches out and pulls data from a massive public database, finding scans that used similar settings to yours. And finally, QM Violin brings it all together, creating these cool visualizations that compare your data to that global standard, so you can see right away if your whole data set is high quality or if you've got a bigger problem. So, when you put them together, these tools create the complete workflow. MRIQC automatically flags potential issues by calculating all those raw numbers. And then QM Tools provides the crucial local and global context to help a researcher make a really informed, data-driven decision about whether a scan is truly good enough for their analysis. It's a really powerful combination that's moving us toward more reliable, more reproducible neuroscience. And it leaves us with a pretty fascinating thought. If we can trust our data more and spend less time worrying about all these hidden flaws, how much faster can we truly accelerate our understanding of the incredible complexities of the human brain?